Section 15.4 Heterogeneous Equilibria. Many equilibria, such as hydrogen-nitrogen-ammonia system, involve substances in all the same phase. Such equilibria are called homogeneous equilibria. In other cases, the substances in equilibrium are in different phases, giving rise to heterogeneous equilibria. For example, consider the equilibrium that occurs when solid lead chloride dissolves in water to form a saturated solution. This system consists of a solid in equilibrium with two aqueous species. If we write the equilibrium constant expression for this process, we encounter a problem that we have not encountered previously. How do we express the concentration of a solid substance? Although it's possible to express the concentration of solid in terms of moles per volume of a unit of volume, it's unnecessary to do so in writing equilibrium constant expressions. Whenever pure solid or a pure liquid is involved in a heterogeneous equilibrium, its concentration is not included in the equilibrium constant expression for the reactant. Thus, the equilibrium constant expression for equation 1518 is equilibrium constant is equal to the concentration of the lead ion times the square of the concentration of the chloride ion, but not divided by the concentration of the lead chloride. Even though lead chloride does not appear in the equilibrium constant expression, it must be present for equilibrium to occur. The fact that pure solids and pure liquids are excluded from the equilibrium constant expressions can be explained in two ways. First, the concentration of a pure solid or a liquid has a constant value. If the mass of a solid is doubled, its volume also doubles. Thus, the concentration which relates the ratio to mass stays the same. Because equilibrium constant expressions include terms for reactants and products whose concentrations can change during a chemical reaction, the concentrations of pure solids and pure liquids are omitted. The omission of pure solids and liquids from equilibrium constant expressions can also be rationalized in a second way. Recall from the last section that what is substituted into a thermodynamic equilibrium expression is the activity of each substance, which is the ratio of the concentration to a reference value. For a pure substance, the reference value is the concentration of the pure substance itself, so that activity of any pure solid or liquid is always simply 1. As a further example of a heterogeneous reaction, consider the decomposition of calcium carbonate. Solid calcium carbonate produces calcium oxide solid and carbon dioxide gas. Omitting the concentrations of solids from the equilibrium constant expression gives the equilibrium constant is equal to the concentration of carbon dioxide gas, and the pressure of, and K sub P, the pressure constant, equals the partial pressure of carbon dioxide gas. These equations tell us that at a given temperature, an equilibrium among calcium carbonate, calcium oxide, and carbon dioxide will always lead to the same partial pressure of carbon dioxide as long as the three components are present. As shown in figure 15.8, we would have to have the same pressure of carbon dioxide regardless of the relative amounts of calcium oxide or calcium carbonate. Figure 15.8, a heterogeneous equilibrium. The equilibrium involving calcium carbonate, calcium oxide, and carbon dioxide is a heterogeneous equilibrium. The equilibrium pressure of carbon dioxide is the same in the two bell jars as long as the two systems are at the same temperature. Even though the relative amounts of pure calcium carbonate and calcium oxide differ greatly, the equilibrium constant expression for the reaction is K sub P equals the partial pressure of carbon dioxide. When a solvent is involved as a reactant or a product in an equilibrium, its concentration is also excluded from the equilibrium constant expression, provided the concentrations of reactants and products are low, so that the solvent is essentially a pure substance. Applying this guideline to the equilibrium involving water as a solvent, water plus carbonate ion yields hydroxide ion plus hydrogen carbonate ion, gives an equilibrium constant of the expression of K sub C equals the concentration of hydroxide ion times the concentration of bicarbonate ion divided by the concentration of carbonate ion.